We're starting the topic now, which is called equilibrium. This is the final unit of the course, and we're going to discuss the mathematics of equilibrium for what's called a point body. And then later, we're going to talk about, and today as well, we'll talk about equilibrium of a rigid body. And then we're going to look at some applications involving trusses and beams. So I'll define what a truss is and what a beam is. I'm pretty sure that you know what the ladder is, the beam there. But anyway, first we begin with something called equilibrium of a point body. So what does equilibrium mean to you? Can you let me know in the chat, what does equilibrium mean to you? Anybody in the chat want to say something there? What is equilibrium? It's very quiet. No movement. Okay, I'll take that. I'll take that. Equilibrium definitely will result in some cases, in most cases, in no movement. If you're talking about a structure, static, similar to Joshua's answer. So as long as the object is not accelerating, it's in equilibrium. But we want something called static equilibrium here. So that's a good answer, Joshua and Jai. Combo there. So basically, equilibrium means that the net force is zero. But it also means something else later. So, whoops. It also means something else later, which I will discuss shortly. So there's one more thing here. Let's just put a question mark, and I will come back to that as we proceed in the class. So our definition for equilibrium is just this, temporarily. So what is a point body? What do you think a point body means? What does that mean, a point body? Well, it just means that all the mass is concentrated at a point. That's all. All of its mass is concentrated at a point. So you've been dealing with point bodies since the vectors units. So we're going to go through questions 1 to 5 and discuss equilibrium of a point body. Here's the mathematics for it in 2 dimensions. So notice that equilibrium can be in even higher dimensions like 3D, but in 2D, that's the math that you need to know. So let's discuss what these formulas mean. So what does this mean to you? Can someone say in their own words what this equation, the first equation, means? Just in your own words, what does that equation mean to you? Okay. Maybe some people are not familiar with this symbol. Thank you, Ravindra, that's it, yeah. So this means the sum. We've seen that symbol before. We've seen it before. That means the sum. So the sum of all of the forces in the x direction have to be 0. And then, of course, again, the sum of all of the forces in the y direction have to be 0. You've inherently done this without using this fancy notation. You have done this before in the notes. So we're going to go through this process and do some questions. There's only 5 of them, and they're really meant to warm you up to the idea of these 2 equations. So let's take a look at the first example. There is no axis assigned here. There's no grid, but we can assign our own grid to the question like that. Oops. There's x and y. And in this case, this is a one-dimensional question. So really, we don't have to say too many dangerous things here. we can say that oops. I'm just going to open the PDF again, the PowerPoint, because it seems to be glitching. Sorry about that. So we only have to look at the x direction here. So the sum of the forces in the x direction has to equal 0. Now there's only two forces acting in the x direction. There is the force to the left, and then there's the force to the right. So if you want, we can say that when you go to the right, the force is positive, and when you go to the left, the force is negative. Or if you don't like that idea, you can actually do it a bit more robustly like this. You can say that the unknown vector f plus the other one, we know how much this is. It's 43.1 pounds of force. And we also know that the direction is to the right. Okay, so that's a vector. That 0 is a vector, but we can be a little bit. You should put an arrow on the 0, but if I don't put it, I'm not gonna bug you, okay? And you won't. You don't have to worry about it either. It's fine. But there should be an arrow on the 0 there. So how do you solve this? Any suggestions on how to solve this equation? How do we solve for f, the unknown force? Any thoughts? Yeah, you just move it over. Thank you, Jai. So Jai is just saying do 0 minus. So you can do here 0. I'm going to put a vector on the 0 because there should be a vector there. It's bugging me. So 0 minus this. And of course, the minus of something to the right, it really just means it's going to the left. Many people in this audience are going to be like, why did this person take so long to answer the question that was so easy? And the reason I did that is because when the questions get more complicated, you understand the basic question and you can build off of that. So, I mean, if this example was on an evaluation of some sort, I wouldn't expect all of this writing. It would be honestly, it would just be a multiple choice question. If it was that, you just 43 to left, right? Like any who feels confident about the answer here and wants to move on now to the next one. Who feels good about this question? Anybody else? Thank you, Sean. So right now I got a few people that seem to be on target, but there's another 16 people. Easy, Nikita. Thank you. Asim. Awesome. All right. So that's about 5 or 6 people. I want to hear from a few more people that they understand this, that they understand the notation. Good to go. All right. Okay, cool. Thank you, everybody. So let's take a look at this next question and see if anything really changes. So we're looking back here, and you can see that what's changed on here is I've introduced a force F2 in the vertical direction. So let's put our axes. Let's put our axes here, X and Y. You know that you can actually put these two axes any way you feel like. You could put them like this, but doing it on some angle of rotation would be really, really inefficient for this question. So, question for you in the chat there. Can I just take this thing here and copy and paste it to right here? Is that true? Can I just copy and paste that down there? What do you think? Can I just copy and paste that? Yeah, you can actually just copy and paste it for F1, yes. So the question I'm asking you now in the chat is, what does F2 have to be? Okay, so F2 has to be 0, but I need to justify that for the class. So let's justify it so everybody is, whoops. Let's justify it so everybody's happy with what's going on here. I'm just trying to line them up a little, make them look pretty. So let's get rid of all this crap here. And now we're going to call this F1, because it is F1, to be fair. I have to write that with the appropriate subscript. And over here, we're going to have F2. Wait a second. Plus what? What the heck's going on here? Is there a force acting anywhere else in the vertical direction? Are there any other vertical forces? So what's the conclusion? I think Jai already wrote the answer there. Yeah, it's 0. F2 is 0. Isn't that cool? That's kind of like, it's kind of like you're probably wondering, and I mean, we're very practical people here. I found over the year that I've learned to get to know you and all that. Um, you know that common sense is really important when you're doing math and physics questions, and common sense would dictate here that you wouldn't want to go through all of this writing. In fact, why would someone even put a force there when there's nothing there? So you're probably wondering, why is F2 in the diagram to begin with? And this is because when you start analyzing more complex structures, there will be forces that there'll be a vector there, or a member in that structure. Like maybe this is a truss, and this is one of the joints, and you will have a zero force. So this is not what I'm trying to say. It's not a dumb question. It's not an unrealistic question. You will see calculations later, not in this course necessarily, but in the fall in semester 3, where you'll analyze structures where there will be a third force like that, and it'll be 0. So remember this pattern. Whenever you see a T shape, see how it's a T shape? Whenever you have a T shape, the odd one here, this guy here, the odd one out, will be 0. So that's an interesting thing to remember from forever and ever when you're doing an analysis of structures, okay? Whenever you have a T shape, that one that acts like that, perpendicular by its own, on its own, I mean, should be 0. So I promised you we'd do 5 of these, and we've already analyzed 2 of them with I'd say decent success. Let me know in the chat. Do you find these 2 questions we did easy? In the chat, easy or annoying or whatever. As you think about that, it's not a tough question. Do you think those 2 questions were easy? Yes or no? So right now, one person has responded, but that's okay. I'm sure more people will chime in a second. Thank you, Asim, and thank you, Sean. I'm just doing some housekeeping here, as you can see, getting ready for the next the next part of the game. So, question number 3. Who thinks they could answer this question in their head? Who can answer this question in their head? I'm going to type in the chat. Yeah, I'm going to put me too. Yeah. Because this question, it's called decoupled. See how the F2 and the 35.6 go together? And then the F1 and the 43.1 go together? Like, they don't mix. So these guys here in the horizontal, they're on their own, and then these guys here are on their own. They don't want to be friends with each other. So they all don't hang out together. They're decoupled. That's the word, okay? Decoupled. Let me write that word here, okay? So mathematically decoupled as well. So if we look over here now, we can do the x direction, and I'll go through it formally. So this is going to be F1 plus 43.1 pounds to the right. And actually, this is the same answer as before, so I feel kind of wasteful. It's okay, I'll just type it out. You know me well enough by now that I like to use repetition when I teach. I find repetition is a little bit boring, but you know what? I'll take boring as long as it's easy and I can understand it. So there's the answer from before. That is an easy question because it's almost like we're building a little bit of a house here, and we're just layering up the floors. Okay, so now let's do the y direction. And I guess there was a typo on the previous page. I should correct that. That was silly. There we go. All right, in the y direction, what's the final answer? What's the final answer? What does F2 equal? With the direction. Give me a direction as well, because it is a vector. Anybody? F2? What is the final answer? Thank you, Sean. 35.6 pounds up. So let's go through the learning steps there. So we would have F2. I don't even care what F2's direction is here. I'm just putting it as a variable, and I'm gonna let the math unfold on its own. That's the beautiful thing about this. You don't have to like assign directions to the variables that represent the forces. You just go with it. Just go with it, my friends. Cruise along, okay? So here we have almost done. It takes me more time to type it than it does to answer it in your head, as you can see, hopefully. That'll be the 0 minus all right. Not bad, everybody, not bad. So we have enough of it here that we can proceed to the next question. So these questions so far have been pretty bland, but now we have a little twist here. What have I done in the next question? Let's look at the picture. It's virtually the same picture, except I've introduced the 51.9 pounds, which is going to influence both F1 and F2. So you might be wondering, what would be a real life scenario here? I really want to say that you can make up all kinds of examples here, but really, as far as you're concerned, think of this as being part of some structure. That's how these diagrams come into existence. Like, let's say that you have a bridge, a truss bridge. I'm just gonna make something up here now. This is gonna be the worst diagram ever, so don't judge me on this one too much. Let's just say that that looks like part of the structure. I'll just do some stuff here as well. So this is part of some greater structure, and all you're doing here is the analysis for the pin here, the joint here, right here. And you can see that there are 5 forces acting on it in their respective directions. And you're in some part of the analysis where you're looking to find what the 2 forces acting to the left and to the into the upward direction are. So let's correct that little thing there. So in this case, I don't really want you to get like all hardcore into the cast rule and the trigonometry. I want you to keep it simple. So when you see this 51.9 pounds, it would make sense if we're going to use the x and y axes aligned to the horizontal and the vertical with respect to our diagram. Then you should take the 51.9 and just kind of break it up here. So this is 51.9. I'm not putting the units, if that's okay. I'm just going to be a little bit lazy there. And this is a right angle triangle. Whoops, a little slow here, and that's 28. So you would go here 51.9 cos 28. And then 51.9 sine 28. Any questions about that? Is left non-negative or right positive in the previous question? So what I'm saying in that regard is that you don't have to say left, you don't have to say negative and positive at all. See, what I'm doing is I'm leaving, when I write the arrow on top of the force here, when I write the arrow on top there, then this thing here is a magnitude and a direction. So if you want, you can adopt a more simple notation like what you're saying. So the way that you would write it in this case would be like this. You would write negative f1 plus 43.1 is equal to 0. That's, if you want to write that down, that's totally cool. And then you move it over and you got your math done. You can solve. But then it's your responsibility to put this as well. So the way that I'm doing it, the way that I'm presenting it here is the most formal way that you can probably do it. This is like the super, super formal way of doing it. And this is the casual way of doing it. But if you did it this way and I did it this way, we're both right, provided that your answer has the magnitude and the direction at the very end. So if the comment is definitely valid, that you can assume the left is negative and the right is positive, or vice versa if you really want to be weird. Sounds good? Cool. So if I'm getting all formal here, okay, cool. If I'm getting all formal here, it's just because I want to show you like the most formal way to do it in terms of like presentation, but you can definitely cut corners in terms of what you write as long as you define left as negative and right as positive. So yeah, that's about it for that one. I'm just trying to reference my own notes as well for a second. Okay, so we're on to this one here, and let's do the analysis for the force in the x direction. I might, as we get into more complicated questions, I might actually just relax my notation as well. But for these easier ones, there's no real penalty for me to do that because I can take the opportunity to show you that notation since the questions are definitely a little bit easier to calculate. So here we have F1 in the x direction plus 43.1 pounds to the right plus, now we're going to do the component of the 51-pound force, 51.19 cos 28 pounds to the right equals 0. Okay, so that's the equation for the x equilibrium. We'll deal with the y equilibrium soon, but I'll just kind of shove it over here for now. Anyway, I might do the y equilibrium underneath, so let's just get this guy out of the way here. It's bugging me. It's taking up too much real estate on this page. There we go. There we go. So, as far as you're concerned, you can just add these together because they're all to the right. So 43.1. Okay, so let's do the extra step here because it does require a calculator. So let's take this here and clean that up. I got 45.8. Someone confirm that, please. Someone confirm that in the chat. Is that a yes? Thank you, Sean. And then you can add these together because they are like terms. They're both to the right. So that's 88.9 pounds. We have here 88.9 pounds. And then you can move over the 88.9 pounds. And then the opposite of right is left. So then you're done. Certainly it's a little bit of a marathon to go through it with this formal notation. And I just emphasize again, you don't have to do it this nicely. As long as you get the right answer, I'm not going to complain. but just make sure that you do show some shred of work, not just the answer. If I just see an answer, if I'm looking at an exam or an assignment, especially an assignment, if it's an assignment, I want to see your method. I don't care about the answer. I want to see the method too. For your reference, on past assignments that I've marked, when a student gives the correct answer but has given no method at all, so if they just wrote down 88.9 pounds to the left, so if they just wrote down this, that's it. I mean, it's the right answer. But if they wrote that down, they get half the marks. So if the question's out of 2, they get a 1. If the question's out of 10, they get a 5. I think that's the fair number to give because I don't know if you did it, if you guessed, if you used technology. I don't know if you went to Wolfram, if you used some type of photo digital math application to take a picture of it. I need to see the method. In the Y direction, we can go through a similar process, and I'll go through that now. So I think it's a fair ask. On a test, you know me well enough that I'm very forgiving when it comes to your tests, but with assignments, I want to see the effort. So in the here we have F2, which is acting in the vertical direction, and then we have 35.6 pounds down. I always write down the stuff that's easy first. Those things are easy. The weird quantity is the blue stuff here, is the components. So we're gonna add, and then that's gonna be I don't know if it'll fit on one line, but we'll try. Good enough. We can get our calculators out now and just type that in there. I did that earlier and got 24.4. Can someone confirm 24.4? Thank you, Jai. Okay, now they're both, ooh, that's down and up. So be careful here. The way you want to do this is you can add them together, but you need to switch one of them. I'm going to switch the smaller one. I'm going to switch the smaller one to a negative quantity. And now you can put them together as one vector. That's 35 minus 24, so that's 11.2. Obviously, you don't have the luxury of copy and paste, so I will definitely give you time to copy this down after. The way that I'm showing you on the screen here really is formal, and I keep on saying that. So like if you're getting intimidated by this, as long as you get the right answer, I'm satisfied. I just want to keep on reinforcing that with you. Get the right answer and I'm happy. But for those that are appreciating it more, like they're seeing this formal notation, I am trying to show you with a more rigorous explanation what's going on. I don't want to just give you a casual, oh, just do it this way and it's pretty easy or whatever. You deserve to see something a bit more formal because there are some very talented people in this audience that would appreciate that. So there's the answer to F2. Can someone confirm they agree with both of these answers? Who agrees with these two final answers? Thank you. Thank you. Thank you, thank you, thank you. So, it's a little bit of writing. Perhaps I can relax a little bit on the next question. So we'll see how it goes. I do have a formal answer that I can present on Blackboard. But anyway, I haven't given any of the variable vectors at an angle, and that's not in these notes. I'm not saying that's going to be on your assignment. I'm just saying like just trying to get you used to the vector calculations. This stuff, honestly, people, is very much a review. So you can even set this one up as a table. You can set up the next one as a table. But anyway, we get to see it in a different light. So let's move on to the next question. So here you have a situation with two forces that are unknown and then some other forces that surround a junction here. And our objective is to find the vectors F1 and F2. So I'm just checking something here. I noticed there's a typo here. Again, this is my first time delivering this book to a live audience. So those should be vectors. I'll make those corrections and put them on Blackboard eventually. But that's okay for now. Moving on here. Why don't we answer this question with a table? Let's answer this question with a table. Perhaps people want to see that. They haven't seen it in a while. We can answer it actually both ways. We'll answer it like the way that I've been showing you, and we'll answer it as a table as well, so that you can kind of see it both ways, the old way and the new way. That's the best thing I think we should do. So in the x direction, how many forces acting in the x direction? Let me know in the chat. How many forces are acting in the x direction? 4 is correct. Yeah, there's 4 forces acting in the x direction. So in the x direction, we have the following. We have F1 plus 51.9 cos 28 and then we have the ones going to the left. Plus 43.1 pounds to the left and 78.1 cos 42 pounds to the left. So there you have it. 4 forces, and 2 of them are components, whereas the other 2 are just the whole quantity. So now your objective is to just clean that all up and express it as one vector, and then you can move on. So let's see what happens here. So this one is going to be 51.9 cos 28 to the right, which I got 45.8. That was from before, actually. And then the 78.1 cos 42 is going to be 58. Can someone confirm those numbers? Okay, thank you. Now you got to add these all up. You got to add these all up here. So we have 2 lefts and 1 right. You notice that the lefts add up to like 101 roughly, and this is only 45. So I'm going to make the smaller one that goes to the right, I'm going to turn that into a left. And now they're all the same, they're all left. So I can add them all together. So if you add those all together, you're going to get 55.3. And then you can move it over. I'm not writing the 0 this time. I'll say it again. You do not have to do all of this writing. I don't care about all this writing. I'm only showing it to be formal and diligent. All I care about is that you do show some calculations to demonstrate your knowledge of components and also to prove to me that you didn't just use technology to solve it without using your own skill. So that's the x component equilibrium, or the equilibrium in the x direction. We can also find the value for F2 by computing the equilibrium, or using the equilibrium in the y direction. So let's do that now. So in the y direction, it's very similar calculations. So we'll go through it nice and carefully as well here. So let's do let's do F2 first, since it's acting down, and I can just get that out of the way. And then everybody else is acting up. So 78.1, 35.6, and 51.9, all of these vectors, either entirely or partially, are acting in the vertical direction. So we'll find, I'm just going to write them down and systematically deal with it. So 35.6, let's put that one first because that one is super easy. And then we can do the other ones as well. So we'll do here 51.9, sine 28 degrees, and that's in pounds up. And finally 78.1, oops, sine 42 degrees, units of pounds acting up equals 0. I'll fix that in a second here. Let me just stretch it out a bit. So from what I understand, you have a very busy week. Is that correct? Lots of exams, lots of fun stuff. Yeah. So that's why I made your assignment very short. Oh, I see. Well, yeah, I'm not going to damage you guys too much today. Don't worry. I hope you don't think that this lesson is exceptionally painful. So these ones are all acting up. So we can get our calculator out here. Yeah. Yeah, I'm just going to say that again. The assignment, if you haven't started it already, it's not a long assignment. It really isn't. I think most people that have looked at it already will attest to it not being a long assignment. Last question's tricky. No, the assignment is not on this. Next week's assignment is. Next week's assignment is. I posted the assignment on Sunday on purpose because that way if people want to get it out of the way, they can get a head start on it in between, like taking a break from studying for the other stuff. So I've got the quantities here. Just gotta get rid of that sign. Did someone confirm those three numbers are correct? Those three quantities are correct? Who agrees with 35.6, 24.4, and 52.3? Thank you, Sean. Okay, so if we put those all together, that's 112. I'm going with three significant digits here. So that's why I'm always kind of just doing that little thing there. So let's get rid of that. We'll have the negative of up. Which of course comes down. So everything that we've done up to this point, you inherently have done before. In fact, your second test had a question involving equilibrium, if you recall. But that was harder than this stuff because you had to solve a linear system, if you remember. So this question here is easier than the question on your second test because the forces are essentially decoupled algebraically. I mentioned that you could use a table to solve this, and you're more than welcome to. The only thing I'll say about the table is I'm not going to use the cast rule. And you know we talked about between 0 and 360. I'm not going to do any of that angles consideration, I would just really simplify the table a little bit here. So let me do the cheap table, and then we can move on. So if we do a table, it's going to involve, I just got to think for a second. Sorry. So there's 5, 3, 6. Okay, so 6 forces. So I need 7. I need 7 rows here. So don't mind me if I zoom out for a second here. So we would have F1. F2, 43.1 pounds to the left, 35.6 pounds up. And then here, the next two, I'm just going to bold that in. These ones here, they're the 78.1 and the 51.9. So I'm not going to write down the standard angle here. I'm just going to say 78.1 pounds. And I'll just say here like left, 42 up. I'm just saying it very like I don't like writing it like that, but I'm just writing it like this just to demonstrate something quickly. 51.9 pounds, right, 28 up. So these are just kind of things that you could say here, but ultimately the x components and the y components. Let's go here. So F1, the x component is going to be plus F1. This is going down to how AO says right is positive, for example. F2 is down, so that would equal the negative of F2 because these are magnitudes. You see how there's no arrows on top of these? There's no arrows on top of these because now I'm just talking about magnitudes only. The negative sign gives you the direction. And then if you have 43.1 to the left, that would be over here. So negative, and I'm not putting units here either. And then 35.6 up would be here, 35.6 up. These are all 0. That's 0, that's 0, that's 0, that's 0. And then we have some stuff here about left and up. So in the 78 case, you'd have here 78.1 cos 42 to the left. And then you'd have 78.1 sine 42. And over here, you would have to the right. Oh, that's to the left. Sorry, there's a negative sign there. The negative to the left. To the right, you'd have 51.9 cos 28. And then that one's also up. So I'm putting these deliberately. That's plus because it's up. That's plus because it's up. This is plus because it's to the right. And over here, this is up. So it's going to be positive 51.9 sine 28. So if anybody in the crowd here prefers the table to what I wrote earlier, this is definitely totally cool to do. But the key thing here is that this is 0. This is 0. The totals are 0 for equilibrium. That's what I'm trying to emphasize here. These zeros here are not cosmetic. They're emphasizing the fact that we have a total of 0 for equilibrium. So let me know in the chat, did you like the formula way or the table way? What do you like, the table or the formula? It gives me insight into how you think. So far students are saying formula, but there's another 16, so there's 13 other people that haven't answered. Okay, so most people are saying formula. So the good news is that it doesn't matter which way you do it, okay? But if you wrote this down, just for argument's sake here, Yeah, the table is definitely a little bit weird. But the cool thing is with the table's nice if you're like if you're trying to do it in Excel or something. So this thing here, if you look at it this way, if you just read it vertically, that's what this is. See that? If you read it sideways, they're the same thing. These arrows here are I'm just showing you that it's the same thing. And this one over here, that if you read it sideways, is this column of the table right here. So really they're saying the same thing. It's just the way that you view it or like to see things. We will be sticking with the formulas though, because we can't really deal with the moments in such a friendly way. There probably is very slick ways of doing moments, but we will need to deal with moments shortly. So it's 8:53. I'd like you to take a break until 9:10 is fine, okay? Just take a break, nice healthy break there, and we'll continue with trusses. So the examples we started with were for a point body. And I mentioned that a point body is a body in which all of its mass is concentrated at a point. Now, in the case of practical application, we know that it doesn't really make sense when you have a structure to assume that all the mass is concentrated at a point. The idea of having something as a center of gravity is important, and you can like model something by putting all of its mass at the center of gravity to analyze some of the equilibrium, but not all of it. So that's why we have to consider things called rigid bodies. So a rigid body, in this case, the rigid body is when you don't have all the mass concentrated at a point. So the mass is distributed. So this is like a little bit more complicated in terms of the math. If we're thinking about two dimensions, you'll see that the formulas look sort of similar. So let's take a look here. We have two-dimensional Cartesian, so 2D behavior. These equations are just the ones that you're familiar with. But the third equation involves the letter m. What does m represent? What do you think m stands for? What does the letter m stand for? Any uh, any brave volunteers there in the crowd? So it's close to momentum. It's moment. Okay. So this one here is the new equation, which just says that the net moment must be zero, and any point. It doesn't have to be. It doesn't have to be at a specific location. The net moment has to be zero about any point. So this is going to be the new thing that you're going to really be focusing on today. This is the tricky part. But once you get past this thing, then everything else is good. Even the remaining material in this chapter, like all of it. So we're going to analyze some trusses today. We'll see how it goes. And then after that, I think that what we'll cover next week, and it won't take us too long next week to do it, you're going to be in a very comfortable position. So what you're going to do now with me is calculate the forces that act externally on a structure using these equations for equilibrium for a rigid body. In order to do that, though, we need to talk about reaction forces. So here's some diagrams that represent how objects and structures connect to each other. So for example, how things are supported can be modeled in various ways depending on context. So let's say that you had the following scenario. Let's say that you had a table here, and then you had another table here, and then you put a book or a piece of wood or something in between the two tables. So this object here is not going to move. It's in equilibrium. And the reason it's in equilibrium is because there are forces acting on it that cancel each other out. See, on this side here, the table's pushing up, and on this side here, the table's pushing up. There is a third force that's acting on the object, which is gravity. Gravity is pulling this object down. So how did I know that I draw a vector here, and how did I know that I have to draw a vector here? So those vectors that I drew in green that I'm circling are called reactions. How do I know to model that interface, that interaction, that way? And the reason is because we have simple templates that we can use here relating to how the real world, how forces interact for reactions in the real world. So for example, the first one we just did right here was the simple one. This is called a simple support, okay? A simple support. So a simple support is modeled by a single force acting perpendicular to the surface. So that's exactly what this example is here. There's also something called a roller support. I'm wondering, let me know in the chat, have you ever seen these things before? Have you ever seen something called a roller support or a simple support? Who's seen these before? Anybody? Tell me yes or no. Have you seen this before somewhere? Okay, so I'll be very careful with you. The good news is, everybody, I don't want you to get too scared because there's only 3 ones that you have to know for me in this course. And I'm just going to keep on looking through here. These are the 3 that you need to know in this course. The first 3, okay? This one, and this one. Any examples that I show you today or next week is going to be these three models. And then these ones here, which are called fixed and cable, they are very important in practice, but we're not going to do them in this course. So I'm putting X's here. You don't have to worry about these 2, okay? But these are just how you model the interaction between a structure and its supports. Whether it's a book resting on the table or perhaps something more complicated. The big distinction here is that when you have a pin support, when there's a pin, there are 2 forces acting here. There's a horizontal and a vertical. And when you have a roller support, there's only the vertical. So the pin and the roller are very commonly used in structures. The simple support, don't worry about it too much. In fact, I think every question that I show you, I'm just going to quickly skim through to make sure that I'm not misleading you there. Just a second, people. Every single question I do with you in this course, every single question is these 2. All you have to know is pin and roller. When you do your next course in the fall, the teacher will get into the other ones. And my objective is just to get you familiar with some of these ideas, not expert at these ideas. So that when you go to the fall, you're like, oh yeah, I remember pin and I remember roller. If you walk out of this course knowing pin and roller, I'm very happy. So just remember, as a template, when you have a roller, you replace it with a single perpendicular reaction. And when you have a pin, then you can model that connection there by 2 forces, one perpendicular and one parallel. I'm not your teacher next semester, Anthony. I don't want to break the news to you. You just broke the news. This, you only have me for a couple more weeks, people. You know, you're gonna make me sad now too. You're gonna make me sad too now. Okay. All right. We gotta suck it up. We gotta suck it up, people. Let's not get too upset that the party's almost over. Believe me, I'm this is hard. This is hard to have the last two lessons and that's it. But even it was even worse last year when I barely got to say goodbye to my students because of COVID. I didn't get the chance to have those last 4 or 5 weeks with them to wrap it up. But anyway, it's been fun. So take a look on this picture here and just give me an insight into how we're going to model this situation. So here we have a truss. Now I haven't defined what a truss is, so I'll go back to a truss. Where's truss? So what is a truss? A truss is basically a structure that is made of triangular sections that are connected by pins. So you see here we have a triangular section connected by pins. So let's see all these black dots here. These represent pin joints. And you can build on them like Lego. See that one there? That's a truss with 2 sections, or 3 sections, or lots of sections. So anyway, we're going to do the analysis for these shapes, these structures. But in this course, we're only focusing on the outside. We're not going to calculate the forces on the inside. Our objective in this course, and I want to emphasize that a lot, we are only doing the reaction forces. Okay? So if you're getting scared about, do we have to analyze all the stuff on the inside? No. Okay? Outside reaction forces only. So nothing dangerous, people. We're only doing the outside stuff. In the next course, you will go on the inside and do analysis there as well. But with me, you're just doing the outside. So when we look at the structure here, we have a force of 20 kilonewtons. So this structure here, this simple triangular shape, is supporting a 20 kilonewton force. Now a truss, we assume here that the mass of this object is small compared to the support, the load that it's going to support. So we're assuming that the mass of this object is small compared to what it's supporting. And that's a very common assumption because trusses are very strong per unit weight. But in real life, of course, you would consider the weight of the structure as well when practical design considerations are evident. Okay, so now we want to find out the reactions. So what you need to do is draw a new diagram, and I'm just going to draw the diagram again here. I'm going to screenshot it from my personal notes. So what did I do there? Just take a look at the 2 pictures and tell me in your own words in the chat, what did I do? I'd like you to use the word replace in your explanation. So use the word replace in your explanation. So in the chat, what did I do? Try to use the word replace. Anybody? No? I guess you really are focusing on your exams this week, and I can appreciate that. That's it. Thank you, Jai. I replaced, this is a support here. So I'm replacing these 2 supports. Whoops, let me draw that better. We're replacing these 2 supports with the reactions. See here? We have Rx and Ra, and then we have Rb. Don't worry about what the subscripts are. Let's zoom in here. Just, there's 3 of them. Why is there 3? Because on this side, it's a roller. See, that's a roller. And I mentioned to you earlier, when you have a roller support, you only put a vertical one. perpendicular to the surface. But when you have a pin, you put a vertical and a horizontal one. I don't say that they're going to be, some of these answers for these reactions might be zero, but the point is that they all must be drawn since they model what they're modeling the physical situation here. So let's write that down. So the first thing you want to do is draw the same structure and replace the supports with the reaction forces. So that's the way that you start off these questions, is get those reaction forces on the diagram. And now it's a matter of applying the principles of equilibrium for a rigid body to solve for the reactions. Now we're going to apply those equations for 2D equilibrium to get those reaction forces. And in this case, I think that you're going to find the analysis is going to be a little bit more relaxed. I'm not going to get as fancy with the notation, but I do think you're going to find that the math here isn't too bad. So what were those conditions for equilibrium? I'm going to just copy and paste them here for my notes. So those are the conditions for equilibrium. I didn't write them in the order that we had. See, I started off with the net force in the x direction, and then I did the moment and then the y. But we'll talk about them and we'll do them carefully here. Okay, in the x direction, how many forces are acting? I want you to imagine, just to be clear here, I want you to imagine that this thing here is a solid object. Just pretend that's a solid object, okay? So it's like a big chunky triangle. So what are the forces acting in the x direction? Can you take a look on the picture? We have 1, 2, 3, 4. There are 4 forces acting on it. How many of these 4 forces are acting in the x direction? 1. Yeah, just 1. Which one is it? Which force is acting in the x direction? Yeah, Rx. So Rx is the only force acting there. So it's equal to 0. That's done. That's one of the answers. So in this case, you might be wondering, why the heck is it 0? Well, it's 0 because there's nothing else there. So you might say, well, why put it there in the first place? Okay, why do we need a pin here? Why do we need a pin here if it's going to be 0? And I'll explain to you why you would put a pin there. Because in real life, if this was a structure, yes, if the force is acting here down, then this will be 0, for sure. But what if this force was not acting straight down? What if it was acting like that? Now, if it's acting sideways, then there needs to be something sideways to fight it. You see that? If this force was sideways, or diagonal even, then there has to be something at the pin here to fight it. That's why you can't have a roller here. If they were both rollers, this thing's going to just drive along like a shopping cart. It's going to literally just drive along here. It has wheels on it, literally. So that's why we have a pin here. So in this very exceptional example, yes, the reaction in the x direction is certainly 0, but in general, it will not be 0. Okay, so we'll do the moment now and the equilibrium in the y. We don't have to answer them in this order. We just have to answer them in some order. So let's do the y equilibrium because that's the one that you're more familiar with. So let's do that equilibrium in the y direction. So in the y direction, we have RA and RB. And you also have 20 kilonewtons down. What's the conclusion here? I mean, you can drop the vector symbols here and just say that RA plus RB equals 20 kilonewtons. Let me know in the chat, Does that make sense to you that RA and RB have to add up to 20? Let me know in that chat, people. These two guys here, RA and RB that are acting up, they have to equal 20. I got Sean on board. Anybody else? Does that make sense to anybody else there that RA plus RB has to equal 20 in order for the y direction to be stable, to be in equilibrium? Okay, I got 3 people now. Mateo, thank you. Nikita, thank you, by the way. Anybody else? Let me know if that, like, if you need clarification on this. Okay. So we have RA and RB, which are acting up, and that has to fight the 20 that's acting down. And the objective of this question is to determine the reaction forces. So we're trying to find the answers to RA, RB, and RX. In other words, we want these 3 guys to solve. We've already solved for one of them, so that's good news, but we don't have the other 2. All we have is an equation here. And unfortunately, at this point, all we know is that RA plus RB is 20, but that is not conclusively going to give us RA or RB. That's why we need an additional equation to figure that out. So, if we go back to equilibrium of a rigid body, and just read this very carefully, read the yellow thing here. For equilibrium of a rigid body, the net moment is 0. Now, the key thing is, the net moment must be 0 about any point. So it doesn't matter which point you pick on the structure or even off the structure. You have to pick a point on the structure as a reference and state that the equilibrium about that point is enforced so that its total moment is 0. So if I go back here, I arbitrarily, you can choose any point you want. I chose A. I chose A because it was easiest to work with it. And I'm saying here that the net moment about A is 0. So what does that mean? Do you remember the definition of moment? Remember, moment was equal to force times the perpendicular distance. And moment can be positive or negative. Who remembers when it's positive or negative? What does the plus and minus mean? Do you remember from our discussion 2 weeks ago? When is a moment positive and when is it negative? Thank you, Jai. So it's positive when it's counterclockwise and it's negative when it's clockwise. So it's positive when it's counterclockwise and it's negative when it's clockwise. That's how we defined it and how most people in mathematics will define it because of consistency with the right-hand rule for the Cartesian system. So let's go back here and talk about the point A. Here's A, okay? So what you need to do is consider the lines of action for each of those forces. So here's the line of action for the 20. See that? And here's the line of action for RB. I didn't really line it up correctly. Let me clean that up for a second here. And here's the line of action for RA, and here's the line of action for RX. So I'm going to write them down, and systematically we'll talk about what the moments are about A. So let's start with RX. So RX, this is RX. So I'll get rid of all those other lines of action. The line of action to A. How far is the line of action of RX to A? How far from A is it? Can someone let me know in the chat? How far is the line of action of Rx from A? Like, is it 5 meters? Is it half of that? What is it? It looks like it's what? How far is the line of action from A? Maybe it's a trick question, but it actually goes right through it. The answer is 0. That's right, Sean. Because Rx goes through A, Rx will not have a turning effect on this structure. If you push on A, Is this thing going to rotate about A? No. If A was like a hinge, and this was like an object that you were trying to rotate it about A, it's not going to rotate. Similarly, RA also passes through A. So the reaction at A times A, the distance to A is 0. So the reason I chose A was because of these zeros. I was trying to do it strategically. If you're not sure which point to pick on the structure, I usually pick the point where the most variables are. So there's two variables here that are forces that represent forces passing through it, and that's a good place to be because then you can make them both 0 for their distances. Let's talk about this guy here, the 20. How far is the line of action for 20 from A? How far is this line of action? It's 3 meters, correct, Sean. Is 20 going to go clockwise or counterclockwise? Does the 20 kilonewton, it goes negative because it's clockwise, yeah. So this is going to be minus 20 times 3. And then finally, we have the RB force here. So RB is going to create a counterclockwise, so it's going to be positive. Let's put RB there. And how far is the line of action for RB? How far is this line of action? How far is this line of action from A? How far is the line of action from A? 6 is correct. And now you can just solve that with algebra. So you can see here that's a very easy math equation. This is like what AO was saying before. Like you can put plus and minuses and not put the arrows. So someone solve that, and I'm going to solve it as well. If you solve it with some basic algebra, you're going to get 10 kilonewtons. You get 10 kilonewtons. And now that you know what RB is, then the rest of the question falls apart because you can plug it in here, and then you can quickly tell me that RA is also equal to 10. So that concludes the question. We have calculated all of the reaction forces. This example certainly is going to be the most scary for you because it's the first time you're seeing the analysis for the reactions of a truss. But when you look at the vertical and horizontal force equilibrium, in other words, this part here and this part here in red, those things I think would be easy for people. And the part that probably is scaring everybody in the crowd, not everybody, is the moment. So what we're going to do today is really emphasize or slow down. We will slow down a lot, I promise you, as we explore each example to come with this moment calculation. So we're going to repeat this again. There's, I'm just looking ahead in the notes. 1, 2, 3, there's 4 more of them. And it'd be amazing if we can get through 3 out of them, if not 4. But we can always finish off the last one next week, which is fine. So that's probably what we're gonna do. I just want to get as much as possible in your head this week so that when I post the assignment on Sunday, you're not going to rely on our class to finish up the assignment. Like you can pretty much do the assignment based on what I show you in today's class and what we did last week, of course. All right, we're going to move on to the next one here. So here we have a more complex truss, but if you look carefully, you'll see here a roller and a pin. So when we model this with forces, we need to consider that as part of our model. So I'm going to just draw the diagram. I'm going to put it up here, possibly. I'll just keep it down here actually. So there's the diagram again. So just quickly, we want to compare the two pictures before I'm going to scroll down in a second. But if you compare the two pictures, you can see that I've replaced the roller with the one force, and I've replaced the pin with two forces, horizontal and vertical. And to be clear here, you need the pin. This time you need the pin because notice that there is a sideways force. So that means it has to be counteracted by some other horizontal force. Since the roller will not accommodate a horizontal force, we need a pin over here. We need a pin somewhere. It could actually be here or here in terms of design, but I've just modeled it with a pin over here. You don't have to design things in this course. I'm not going to ask you where do you put a pin or a roller. I'm going to give you a picture like this and just say do something with it. So don't worry about that. Now, we're only dealing with the external stuff. So as far as you're concerned, this parallelogram shaped structure, you're not looking on the inside. Just pretend that's one big chunk of metal. As far as you're concerned, this shape here is rigid. It's just a big chunk of metal. And also assume that the mass is small relative to the external forces. So as far as you're concerned, your goal is to just solve for these guys here. We can get very far with the algebra based on just the force calculations. So let's do the force equilibrium first and see if we can set up some equations. I'm not gonna write the vector symbol as much, as you'll see as I do these questions, because now the questions are getting a little bit intense. I guess it doesn't like me putting an arrow. Well, that's exciting. There we go. So the net force in the x direction has to equal 0. So which forces are acting in the x direction? How many forces are acting in the x direction? Let me color in all the forces so that you know that we have them all accounted for. There's 5 of them. So which of these 5 forces are acting in the horizontal direction? There's 2 of them. Yeah, which ones? Give them a name. Tell me a number or a name for them. $15 and Rx. And that's perfect. So we can actually see here that we have, so we can see that Rx is equal to, or Rx has to be 15 kilonewtons to the right. There's no choice there. Rx has to be 15 kilonewtons to the right. I hope that that's crystal clear. And we can also work in the y direction as well. So if we go in the y direction, we can see that in the y direction there are 2 forces acting down and 1 force acting up. So in the downward direction, we have RA and RB. No, can you see me still? Can you see the screen well, people? Okay. All right, so we have RA and RB. It's frozen. Let me unshare it and then share it again, okay? Can you see it now? Do you see my mouse moving? No? Some people say yes, some people say no. Yeah, maybe if you can't see it, log out and log back in. Leave and come back, okay? I'll just wait for those that are still here. I'm just going to wait for people to show up. Thanks, John. Yes. Is it working? Is it working, Joshua? Okay, good. Yeah, okay. That's what John Sawicki was saying that. The refresh. Yeah. Okay. Anyway, I'm just gonna I'll do this really slow, so people are gonna pop back in and out here. They're not missing anything. So algebraically, we have that RA and RB have to equal 20. Now, as a vector, that was exciting. Let me write it down better here. So we're kind of stuck at this point because we don't actually have the answer for RA and RB. We do have RX, like I can highlight that in blue and call that one done, but we don't have A and B. So that's why we need an additional equation to achieve that. So what we're going to do again is we're going to use the moment equation to set up a new equation or a third equation. So the moment balance equation or the moment equilibrium equation will give us another equation. That's the idea, okay? We can pick any point we want. So I'm gonna find the moment about A, okay? I'm gonna use the point A again. So I'll use the point A, and the reason I chose A, I mean I could have chosen B as well, but I think A is just as fine. So we have the net moment about A is equal to 0. So here we go. We need to calculate the moment that each of these forces generates around A. So let's start with RA. RA passes directly through A. So RA, its line of action is going to be 0 distance away, so therefore it produces no moment. Let's do RB now. RB is here. RB is going to be clockwise. You see RB here is going to make it turn this way. It's going to turn that way, so that's clockwise. So that's minus RB. And RB is at a distance of 6 meters. Its line of action is 6 meters away. Next we have RX. RX, line of action, passes directly through A. So that's why it's just going to be Rx times 0. So this step here that I'm doing by hand is definitely the hard step. That's why I'm doing it by hand and I'm going slow with you so that you can understand it better. We're almost done. I'm just going to squeeze that along here because it's a little bit of writing. Definitely faster to type this, but that's okay. Now we have to deal with the 15 and the 20. I'll deal with the 15 first. Here's the 15. The line of action for the 15 is 5 meters away. The 15 is going to make it go counterclockwise, so it's plus. So it's 15 by 5. And I'm avoiding writing the units, but you understand that the units are very important. Also, the 20 is here. It's 3 meters. Half of 6 is 3, and it's counterclockwise. So that means it's 20 at 3. 20 at 3. So plus 20 times 3. Now when I do this equation here, I should be putting vectors, but I'm being a little bit relaxed about it because moment calculations are scary, at least for like people that see it for the first time. So that's why I'm just being a little bit like relaxed about how I write it. So anyway, you have a beautiful little algebraic equation here that you can solve now. So let's just write it down again. Negative 6 RB plus 75, 15 times 5, and 60. is 0. So you are more than capable of solving that. So what's 135 divided by 6? I did that earlier and got 22.5 kilonewtons. So now that you have that, you're almost done the question. So let's take a look here and see what the heck happened. We have RB is 22.5, and then RA. What the heck happened there? Do you see something? What do you think? Let me know in the chat. Do you see something weird happening here with the numbers? Is anybody feeling a little bit kind of shocked? Look at this. Okay, let's color. I'm gonna color it in red because it is a little bit weird. There's nothing wrong, I promise you. Mathematically, everything we're doing so far is fine. But take a look at this equation here. So we have this equation here in red, and then we have this equation here in red as well. So what's the issue? Can you let me know in the chat? What do you notice mathematically happening here that's a little bit weird? If I plug in 22.5 into this equation for RB, what does RA become? It becomes negative, yeah. So we have RA plus 22.5 kilonewtons down equals, let me write that down here, sorry. This answer is done, by the way. I mean, RB is done. This is down. So we have 2.5 kilonewtons up. So RA is actually up, which is kind of funny because it's drawn down here. You see how we drew it downward? So the diagram had RA acting down. So I just want to say that here while this thing saves. Sometimes when you make an assumption, your assumption's wrong. And that's okay. It's not a catastrophe. You don't fail. It doesn't mean anything. Think about in your life doing algebra questions. How many times have you done an algebra question in your life where you made an assumption and then when you got the answer, it was backwards to what you thought? I've had it happen to me hundreds of times. You know, I'll say let x be this, and I'll assume that x is positive, and then I get my answer and x is negative. I'm not wrong. It just means my assumption was backwards. So this diagram, when you have a pin and a roller, if you're not sure which way to draw the arrows, don't worry. Draw them a certain way, and if the answer comes out as a negative, it means that you drew it backwards. It doesn't mean that you throw your answer in the garbage. In fact, like if this is a test question, don't erase everything and start over again. Just say, oops, I should have drawn it upwards. Big deal. Okay? I want to emphasize that. Just because we get a negative answer doesn't mean that we screwed up. It just means that the diagram could have been drawn better. But as long as you're consistent with how you draw the diagram and how you execute the mathematics and the algebra that follows, it doesn't matter. You just have to take a stand and just make that diagram a certain way and just use it. So don't erase it. Don't say I'm wrong and oh, I have to start all over again. Even if it's your assignment. I mean, for an assignment, you could obviously have the time to. But if you're writing an evaluation like a test, you have no time to go back and erase the whole question. So just keep that in mind, everybody. I don't want anybody to get panicked because they get a negative and they think that they've ruined everything and they can't, it's wrong and they're going to fail or something. That's not the issue here. Okay. I say that we do one more question. What do you think? One more question, people? Or do you want to take a break? Your call. Do we do another question or do we take a break? Okay. Well, I got a couple people saying one more. Let's do another one. Okay, let's do another one. Let's do another one, okay? Yeah. So number 8. Hopefully you're getting the hang of this. Really, there is no other twists and turns. It's just draw the picture, draw the reactions, and forces and then the moment calculation at the end. And pretty much everything the same every time. So I'm going to really try to relax my notation for this question so that you don't think that it has to be like super complicated. So step one is we're going to replace the pin with 2 forces and the roller with just the 1 force. So I'm doing that right now. So there's the diagram. Notice here the pin at A, I've replaced it with 2 forces, and then the roller, I've replaced it with 1 force. So we can draw the reactions now. So there's a reaction here, here, and here. And then we have these additional forces here, which are our inputs to the problem. In this question here, we can clearly see that in the x direction, there's only 1 force acting. You see that? This guy here, Rx, it's by itself. There's no other forces acting sideways. So for that reason, it's just 0. So there's no real there's no real danger there. It is what it is, okay? So that's the net force in the x direction being in equilibrium. We'll do the equilibrium for the y direction now. So in the y direction, I'll write down the math underneath in a second. In the y direction, you want to look at what forces are acting up and what forces are acting down. In this case, there are 2 forces acting down and there are 2 forces acting up. We assume that RA and RC are acting upward, and if we get a negative answer, it just means our diagram was backwards. But that's okay. So I'm going to do this one a little bit cheaper than I did the other questions today, that is. I'm just going to say that RA plus RC has to equal 40 plus 40. Let me know in the chat. Does that make sense that RA plus RC has to equal or counteract the 2 40s that are going down, that are acting down? So you can just write that down. You don't have to be pretty. Like, you don't have to put all those vector symbols that I'm writing. It's all good, man. All good, okay? So we have RA and RC is equal to 80 kilonewtons. So that's what we have so far. But now we need another equation. So it's kind of what I was saying again. We need an additional equation to complete this question. We need an additional equation. So we're going to use the moment about A, just because I arbitrarily chose A. But it's not really arbitrary, I should say. It's because A has 2 forces acting through it. So that means that when I do the math for it, it's a little bit cheaper. So let's take the net moment about A. So you see how this is now our third situation of doing this. So hopefully you're starting to see that it is a procedure that you can get comfortable with. The net moment about A is 0. So if we look here, Rx and Ra go through it. See that? Rx and Ra, they pass right through. So it's Rx times 0 right off the bat, and it's Ra times 0. You don't have to write those down because they are 0. But let's talk about the ones that are not 0, because those are the ones that I care about, because we have to do math with those. So let's take a look here. We have the 40. This 40 here is going clockwise. So it's 40 negative direction, and it's 3 meters from A. This 40 is 6 meters from A, and it's also clockwise. And then we have RC, here's RC, who's also 6 meters, but this one's going counterclockwise, 6 meters. So it's plus RC at 6. So it's plus RC at 6 meters. So we have enough information to proceed in the question now, because it's just one equation with one unknown. So look at that. Looking good now. Minus 120 minus 240 plus 6 RC equals 0. I'll leave the algebra to you for this. This is pretty easy algebra. So someone confirmed they got 60. Can someone confirm they have 60 as well? Thank you, Sean. So see this equation here? We got this guy here, which I'll just make it blue there, and then we have this guy here. So we have enough information to finish the question now, because you can go back to the, and you can say that RA equals 20 kilonewtons. Because you know 60 plus 20 is 80. So final answer, we can take those two things there. Whoops, I lost my screenshot. There it is. And I'll just plop them down here in the corner. So there is the setup for the answer. So one more question. We have a more elaborate truss this time. 3 forces acting in the center, and then you have the pin and roller support over here. See the pin? Whoops. Have a pin here, roller here. So the pin is going to have 2 forces acting this way, and then the roller will have the 1 force acting there. I'll provide you with a separate diagram so that we are not cluttering the original diagram too much. So here's the modified diagram. This is the free body diagram, or the force diagram. And you can see here there are 6 forces acting on this structure. We are only interested in the outside forces. We're not talking about the inside reactions, just the external supports. Upon inspection, can someone tell me in the chat, what does Rx have to be here? What does Rx have to be? 0. What's your reasoning for that, Sean? Right? Give me a sentence there. What's your reasoning for why it's 0? So that your classmates can understand possibly better. No pressure.
I can't be bothered typing it. It's because one's a roller and the other's the point, and
Yep.
so it's not gonna move, so it has to be 0.
Yeah. It can't move horizontally because it's in equilibrium, and since this pin here is the only force that's horizontal in the entire diagram, there are no other horizontal forces. Yeah, it's not going to move. It's got to be 0. So the question arises. People will say, well, why the heck are you putting a pin there when it's not going to move sideways anyway? It's in equilibrium. And the response to that question, if anybody asks you, or in the future, professor or in practice, says, hey, why do we have a pin here? Who cares? Well, the reason is because there could be a horizontal force somewhere else. Let's say that this is the loading. Okay, remember this, for example, could represent a bridge, a support for a bridge. And there are going to be side loading, whether it's an action reaction from a vehicle loading or unloading on the bridge, or maybe it's a wind. Maybe there's wind loading. Wind loading doesn't happen up and down. It happens sideways, or even up and down, or a combination thereof. So you need to allow for the structure in this design to have flexibility. There's other reasons mathematically, but really the common sense answer is you need a pin there in case there's sideways forces. That's just the short answer. So now let's talk about the reactions in the y direction. So in this case here, to spare you having me type in front of you, I'm just going to write down the equilibrium for the y direction, and it's just here. So let's take a look at it piece by piece. Maybe I'll edit this out of the video, don't worry. So there's a net force in the y direction. Gotta love video editing, eh? So the bottom line is that this equation here, most of you could have deduced that based on common sense. Because if A is acting up and E is acting up for the reactions, and these guys here in the middle, all these ones that are known, are all acting down, and they total 100 kilonewtons, then the other guys that are acting up, the RA and the RE, those forces have to total 100 as well. So really, the stuff that I'm showing you thus far in this example and in the previous 3 truss examples, they all are consistent with skills that you could have used a month ago or even before your second test. So this stuff here, although it looks scary and complicated, this is stuff that even if I could have given this on the test, I would never do that to you, but I could have given this on a test too, and half the class would have got it right, and the other half would have got close. I'm not talking about the full answer. I'm just talking about these 2 equations here. So I think that anyway, whoops, I'm trying to just combine all of those. Just make it look a little bit smaller. There we go. So now we need another equation because RA and RE are not known yet. All we know is the relationship between them, but not an absolute. We just know a relative amount. So we're going to go over here to the diagram, and we're going to use the moment calculation about a point to find out the final answer for RA and RE. Now you can find the moment, and this is insane, people. You could find the moment about A, B, C, D, E, F, G, H. You could even find the moment about here, out in space over here. It doesn't matter which point you pick in the universe, it will always give you an equation that will be useful. But we're going to pick the point A because A has the most variables or component variables that are going through it. So it just makes the math a little bit easier. So let's go through that process together, and we can analyze and create an equation. So we're going to say here that the net moment about A has to be 0. In this case, the lines of action of Rx and Ra are 0, so I'm immediately going to just write Rx times 0. And you don't have to write these guys down because they're obviously going to produce no moment. So most people, they don't write them down at all. But, you know, someone like me who likes to program a lot, I like to write everything, even though it's a 0 anyway, because it's just back in my math and computer programming experience. Anyway, here's the 30. 30, whoops. The 30 kilonewtons is clockwise. So is the 20, and so is the 50. The only difference between the 3 of them is that they're different distances. So the 30 is negative and is at a distance of 4 meters. The 20 is also negative, and the 20 is at a distance of 8 meters. And the 50 is also negative because it's producing a clockwise moment, and the 50 is 12 meters away. As you know, the further away you get from the point of rotation, the more impact this distance has. That's why these are growing. I mean growing in magnitude, because obviously they're negative. And then RE, finally, how far is RE? How far is its line of action from A? Well, let's take a look. It's this. So that distance is 16. So that's positive because RE is making it go counterclockwise, and it's RE at 16. And there you have it, everybody. You have an equation now that you can solve for the component, the reaction, at E for the roller. So let's write down what we have here. We have, let's see, minus 120, minus 160, and then fifth 12 is 600. So minus 600 plus 16 RE is 0. I'm just going to write down the answer. This is easy math for people here. This part here at least. You should get 55. And then you can go back. I'll just say here, go back. And you can get RA equals 45. So that's the setup, and I'll just report the two answers. Notice how both answers came out positive. Since RE and RA are positive, it means that our assumptions for the directions for the reactions were correct. So we assumed things correctly. But let's just say someone randomly said, oh, maybe RA is down. Let's say they drew RA in a downward sense. Then what would happen is you would get a negative answer here, and you'd say, oh my goodness, I should have drawn it up. But you don't throw away your answer. You just report the answer. See, all I care about is this. This is the bottom line is, I care about your method for sure, but all I care about is that you get this thing reported correctly. These things in green represent the final answer. Okay, well, not all of this thing here. I'll color the whole thing in green, but all I care about is the R part. So those things in the green highlight are really just the ultimate answer there. So there you have it. That's enough for trusses. And I will leave you with example number 10. You can do that one on your own, and I'll put it on Blackboard, the answer. So be prepared for this Friday. Remember that you have to do it's not a long assignment, but it's still due on Friday. And it's due at midnight. So I put midnight because people say, is it 9 o'clock or 8 o'clock or whatever? With my students in the diploma program, I just said, you know what? Let's make it 11:59 p.m., essentially midnight, so that you can just have the whole day. Because in the past, I've had students say, sir, I didn't know what time it was due or whatever. Like, let's not worry about that too much. Anyway, that's all I have for you today. Hopefully you do well on your other tests, and you can take some time on your own to reflect on this stuff as well prior to meeting next week.